Thank you for joining the team session. Year 13, Applied Chapter 4, Moments. We're going to look now at Section 3, Equilibrium. You've seen before that if the forces in one direction are equal to the forces in another direction, then your resultant force is 0, so your object will not accelerate in either direction. It's exactly the same in moments. If your turning forces clockwise are equal to your turning forces anti-clockwise, your resultant is 0, so it's said that the object is in equilibrium. Okay, let's have a look at the slides. Okay, yeah, so the key bits from here is the resultant force in any direction is equal to 0, and the forces are in equilibrium. Your up forces are equal to your down forces, which you did last year. Same true for moments. If the clockwise moments are equal to the anti-clockwise moments, then the object is in equilibrium. It's not going to rotate in either direction. So quite often in a question, you're going to have to use both of these things to find unknowns and to solve problems. Okay, there's an exam question for you to have a little look at. If you'd like to pause me for a few minutes, have a go at the question, and then I will go through the answer with you. Okay, first thing you've got to do is pull out everything from the question into your diagram. A really good diagram is key to solving any mechanics problem. So put everything on, all your distances and all your forces that we've got there in the question. Draw them all onto your diagram. There's a couple of different ways we could solve this. The first one, we could look at the moments about the pivot. So if I take you through each of these individually, we've got this 20G force there that's 1 meter from the pivot, and that's going in a anti-clockwise direction. I've got the 70G force there, which is a distance of 10 meters. The line of action of the force from the perpendicular distance from the pivot is 10 meters. So that's 70G times 10. Again, that one's going in an anti-clockwise direction. In the clockwise direction, we've got Tom. We don't know what his mass is. His weight is going to be the unknown mass times G. The perpendicular distance from the line of action of the force is 8. So it's going to be 8 mg. I've got an equation there. I've got one unknown, which is the mass. So if I rearrange everything on the equation, I can solve to find that Tom's mass is 90 kilograms. And then what I could do is, because I know it's in equilibrium, I know that the forces going upwards are going to be equal to all the forces going downwards. So the only force that I've got going upwards is the reaction force on the seesaw. So that must be equal to the sum of all these forces going downwards. Lewis's weight, there's 20G weight, and also the Tom's weight. So the reaction force is equal to the sum of all those forces going downwards, which is 1,764 newtons. Okay, we can take moments about any point that you want. We've taken moments about the pivot. If you would prefer, you could take moments about where Tom is. So from where Tom is, because his weight is going through where Tom is, there's no perpendicular distance, so I don't need to worry about the M this time. The pivot is 8 meters away, and the reaction force is going upwards. So I've got a perpendicular distance of 8 meters from the line of action of the force. So that's 8r. It's in equilibrium, so his clockwise moments are equal to his anti-clockwise moments. I've got this 20G, which is 9 meters away, and this 70G, which is 18 meters away. So put all those into the equation. The only thing that's unknown is the reaction force. So I can rearrange the equation and solve for the reaction force there. Again, I can equate forces in the vertical direction. This time, I know what the reaction force is with this method. The only thing I don't know is Tom's mass. So if I do my down forces are equal to my upward forces, because I'm in equilibrium, and solve it, then I work out that the mass must be 90 kilograms. Okay, another one. Pause me, have a go at this, and then I will talk you through the answer. Okay, let's have a go. So what we've done here is we've resolved vertically, made sure that all the forces, everything in the text, we've included in our lovely diagram. It's absolutely essential that you include everything on your diagram. So vertically, I've got all my reaction forces going upwards. I've got the mass of the man and the mass of the beam going downwards. And I can rearrange and solve to work out what my reaction force is. It's 40G. Yeah, it's not giving us any distances anywhere. So we're going to introduce a variable x. So we're going to say that this man is x meters. The way they've done it here in the question, there's lots of different ways of doing it, but they've said he's x distance away from point A. Okay, the reason I've done it that way is because we're trying to find the distance from A to E. So it sort of makes sense to define his distance as a distance away from A. So if we take moments from A, again, you can take moments from absolutely any point that you want, but because we're trying to find the distance from point A, it just makes life a little bit easier as we use that the point that we're taking moments from. So from A, I've got my reaction force 1 there, which is 40G, and that is at a distance of 1 meter. That's going anti-clockwise. I've got my reaction force of 2R, which is 80G, and that is a distance of 4 meters. Okay. I have got going clockwise, I have got my center of mass of this beam of 40 kilograms at a distance of 2.5 meters. So it's 40G for the force times a distance of 2.5. I've got the man whose mass is 80G. The distance away is x, the distance from A to E. That's the only unknown. So I've got an equation there. I've got one unknown. So all I need to do is rearrange and solve the equation to find out what that missing distance is. And an exam question we've got from the old Edexcel 2013. If you can have a little go at that one for me, please. If you pause the video and then I will go through it. Okay, first thing, like last time, we need our nice little diagram with all the different forces being shown on our diagram. So we've got a reaction force at C, we've got a reaction force of 2R at D. We've got that because it says the reaction on the rod at D is twice the magnitude of the reaction at the rod on C. So all I'm doing is everything from the question. I'm told the uniform rod's 2 meters and it's got a mass of 50 kilograms. So I've got my 50 kilograms acting in the center of the rod. So that's at a distance of 1 meter from each end. It defines x as the distance from D to B. So from the distance the pivot is from the end of the rod on this side. Because the rod is in equilibrium, I know that the clockwise and anti-clockwise moments are equal. I also know that the forces in any direction are equal, the sum of the forces in any direction are equal to 0. So if I look at the sum of the forces vertically, I've got R and 2R going up. The only force I've got downwards is the weight of the rod, which is its mass times G, so I've got 50G. For my moments, I can go about any point I want at all. In this particular question, they've taken the moments about C. Don't need to worry about that R there because it's going through the line of action. So all I've got is going in a clockwise direction. I've got my 50G times the distance of the line of action of the force, the perpendicular distance of 0.8. And then going in a anti-clockwise direction, I've got my 2R. I know that the distance to the center of the rod from B is 1 meter. I know the distance from B to D is X. So that's 1, that's X. So this bit here between D and the center of mass must be 1 minus X. So the total distance from A to D is going to be 1 plus 1 minus X. Sorry, I'm taking moments about C. So the distance is going from C, 0.8 plus 1 minus X. So 0.8 plus 1 is 1.8 minus X. So my total distance is 1.8 minus X. The force is 2R. So I again get an equation there. From part 1, I can solve to find out what R is. I can substitute my value of R into this for part 2, and from that I can work out what my distance of X is. For part B, I've got a different rod now. So I've got the same rod, I've just placed a mass on the end. Okay, so again, the first thing is I've got to put in all the information that I've got onto my diagram. You're told magnitude on the reaction of the rod at E is 4 times the magnitude of the reaction at C. So I've got an S going up there. They've just gone alphabetically R, so they've called the next reaction force S. So I've got an S there. That's 4 times as big. So that's 4S. You're told from E to B is 0.4 meters. This time you weren't given that last time. So the end of the rod to the center of the rod is 1 meter. So if that's 0.4 meters, that must be 0.6 meters. Okay, so putting everything into action, again, I'm going to look at the forces going vertically. So going up, I've got an S and a 4S. Going down, I've got the weight of the rod, 50G, plus I've got this mg. So altogether, I've got 50 plus mg going down and 5s going upwards. Because they're in equilibrium, the force upwards must be equal to the force downwards. Now I can look at the moments. Again, I can take moments about absolutely anywhere that I want. On this particular question, they've taken the moments about B. An advantage of taking moments about B is that I don't need to worry about this force mg because the line of action of the force goes through B. So there's no perpendicular distance. So we don't need to worry about that force at all if we take the moments about B. So I've got my 50G, which is at a distance of 1 meter. So that's going anti-clockwise. I've got my 4S, which is a distance of 0.4 going clockwise. I've got my S, which is at a distance of the 1 meter to the middle plus the 0.8, so 1.8, going clockwise. So altogether, if I work these out, my only thing that I don't know in that equation is S. So I can solve that to find out what S is. Once I've solved that to find out what S is, I can substitute my value of S back into the previous equation. Then I've only got one unknown, which is M. So once I've substituted back in for S, I can work out what my other unknown is M, and solve my equation to get the value of M. Okay, I'll let you have a go at some of those now. So it's from exercise 4C. It's you've got to do 1 to 8. The bonus is 9 to 11. Thank you for listening, and I will stop the call now.